Alex, the area cheerleader, talking to you about SIMILAR, figures. First vocabulary term is a ratio. That would be a comparison of two quantities using division. So down here you can see 4 examples of ratios written in different ways. Here we have A over B. Here we have 3 to 4. Here we have 50 miles over 1 hour. Here we have $20 per pound. Each of those represents a comparison of two quantities using division. The next vocabulary term is a similarity ratio. That would be the ratio of the lengths of the corresponding sides of a polygon. This is also known as a scale factor. So when given two similar polygons, like these two similar quadrilaterals here, ABCD and EFGH, if you want to create a similarity ratio, you just create a ratio of their corresponding sides. So the measure of segment AB over the measure of segment EF, that ratio would be considered a similarity ratio. And we know that these two sides correspond with one another because of this similarity statement right here. AB corresponds with EF. Now, whatever that ratio is, when you simplify that down, it should equal the ratio generated by the other 3 pairs of corresponding side lengths. All of those similarity ratios should be equal when you simplify them down. Now, it's important to note that we also refer to the similarity ratio as the scale factor. That'll come up today. Next, we're going to talk about the perimeters and areas of similar figures. So this says if the similarity ratio or scale factor of two similar figures is A over B, then A over B is the ratio of the perimeters, and A squared over B squared is the ratio of their areas. So what is this saying? Well, it's saying that if you have two similar figures, like we do here, two similar parallelograms, ABCD and EFGH, if I want to create the similarity ratio or scale factor, I just create a ratio of two of their corresponding sides. So I see that segment AD would correspond with segment EH. So if I create a similarity ratio with those two corresponding sides, I get 12 meters over 8 meters, which simplifies to 3 over 2. That would be the similarity ratio or scale factor between these two figures. Now what this up here is saying is that if I were to find the perimeters of both of these similar parallelograms and simplify that ratio down, it would be the exact same ratio as my similarity ratio or scale factor, 3 over 2. So if I were to find the perimeter of parallelogram ABCD here, it would be 42 meters. If I were to find the perimeter of parallelogram EFGH here, it would be 28 meters. And 42 over 28 simplifies down to 3 over 2. And you see that it does in fact equal the exact same ratio as our similarity ratio. Now last but not least, this up here is saying that if I were to find the area of each of these similar parallelograms and put them in a ratio and simplify that ratio down, it would be equal to A squared over B squared, the square of our similarity ratio. So we can check this out by finding the area of parallelogram ABCD, which is 12 times 6, which is 72 meters squared. We can do the same thing with parallelogram EFGH. The area of this parallelogram would be 8 meters times 4 meters, which is 32 meters squared. We put that in a ratio, we simplify down, we get 9 over 4, which does in fact equal 3 squared over 2 squared, the square of our similarity ratio. She's a home run hitter. Scoot back, way back for example time. Now example 1 says for each pair of similar figures, find the ratio of their perimeters and the ratio of their areas. We're going from large to small. Now as you just saw, both the ratio of the perimeters and the ratio of the areas are based on the similarity ratio or scale factor. So we need to find that first. To find the similarity ratio or scale factor, all we have to do is set up a ratio with one pair of corresponding side lengths in these similar figures. And since we're going from large to small, we want the side length in our larger figure in our numerator and the side length of our smaller figure in the denominator. So to find our similarity ratio or scale factor, we set up that ratio of the corresponding side lengths. It's going to be 4 inches over 2 inches, and we need to simplify that down. So what is 4 over 2 simplify down to? 2 over 1. This would be our similarity ratio. Now, if you recall, we are finding the ratio of the perimeters and the ratio of the areas. So how do we do that? Well, let's first start by finding the ratio of the perimeters. Remember, the ratio of the perimeters is actually equal to the similarity ratio or scale factor. So we say that the ratio of the perimeters is also going to equal 2 over 1. Again, what this is saying is that if you were to find the perimeter of this large quadrilateral and put it over the perimeter of this small quadrilateral and simplify that ratio down, you would get 2 to 1. Next, let's find the ratio of the areas. So the ratio of the areas, recall, is the similarity ratio squared. So we're going to square the numerator and denominator here. What is 2 squared? That's going to be 4. What is 1 squared? That's going to be 1. So the ratio of the areas of these two similar figures would be 4 over 1. Again, what this is saying is that if you were to find the area of this large figure and put it over the area of this smaller figure and simplify that down, you would get 4 over 1. Part B, doing the same thing. In order to find the ratio of the perimeters and the ratio of the areas, we got to start by finding the similarity ratio or scale factor. To do that, we're going to create a ratio with one pair of the corresponding side lengths here. And because we're going from large to small, we need the side length of our large figure in our numerator and the side length of our smaller figure in the denominator. So in order to find our similarity ratio, we create that ratio of 25 feet over 15 feet and we simplify that down. So 25 over 15 simplifies down to 5 over 3. That would be our similarity ratio or scale factor. Next, we need to find the ratio of the perimeters. So recall, the ratio of the perimeters is equal to the similarity ratio. So we know the ratio of the perimeters is also equal to 5 over 3. Meaning, if I were to find the perimeter of this larger triangle and put it over the perimeter of this smaller triangle and simplify that ratio down, it would equal 5 over 3. Lastly, we need to find the ratio of the areas. So the ratio of the areas we know we find by squaring the similarity ratio or scale factor. So what is 5 squared over 3 squared? That's going to be 25 over 9. So what this is saying is if you were to find the area of this large triangle and put it over the area of the smaller triangle and simplify that ratio down, you would get 25 over 9. I say you try, you say you try, you try.
You try.
You try.
You try.
Okay, doing the same thing. We want to find the ratio of the perimeters and the ratio of the areas. In order to find those things, we need to first find the similarity ratio. So the similarity ratio or scale factor we find by creating a ratio of one pair of the corresponding side lengths. And since we're going from large to small, we want the side length of our larger figure in the numerator and the side length of our smaller figure in the denominator. So we can find our similarity ratio by creating the ratio 9 centimeters over 3 centimeters and simplifying that down. So what does 9 over 3 simplify down to? That would be 3 over 1. That is our similarity ratio or scale factor. Next, we want to find the ratio of the perimeters. Remember, the ratio of the perimeters is equal to our similarity ratio or scale factor. So the ratio of the perimeters would be 3 over 1. Meaning, if I were to find the perimeter of this large quadrilateral and put it over the perimeter of this small quadrilateral and simplify that ratio down, I would get 3 over 1. Lastly, we want to find the ratio of the areas. Remember, the ratio of the areas is just equal to the square of the similarity ratio. So I'm going to square the numerator and denominator in my similarity ratio, and I end up getting that the ratio of the areas from large to small here would be 9 over 1. Meaning, if I were to find the area of this large quadrilateral and put it over the area of the small quadrilateral, simplify that ratio down, I would get 9 over 1. Part B, doing the same thing, we want to find the ratio of the perimeters and areas. And in order to do that, you need to first find the similarity ratio or the scale factor. To find that, what you need to do is set up a ratio with one pair of the corresponding side lengths here. And since we want the ratio to be large to small, we want the side length of our larger pentagon over the side length of our smaller pentagon. We then simplify that down to find our similarity ratio or scale factor, and we end up getting 4 over 3 as our similarity ratio or scale factor. Now we can use that in order to find the ratio of the perimeters, because the ratio of the perimeters is equal to our similarity ratio or scale factor. So our ratio of our perimeters would also be 4 over 3. Meaning, if I were to find the perimeter of the large pentagon and put it over the perimeter of the smaller pentagon, simplify that ratio down, I would get 4 over 3. Lastly, we want to find the ratio of the areas. Remember, the ratio of the areas is equal to the square of the similarity ratio or scale factor. So what is 4 squared over 3 squared? That's going to be 16 over 9. Meaning, if I were to find the area of the large pentagon and put that over the area of the smaller pentagon, simplify that ratio down, I would get 16 over 9. Now example 2 says find the similarity ratio, ratio of the perimeters, and ratio of the areas for each pair of similar figures, small to large. Now as you can see in our example down here, we're still given two similar figures, but instead of being given corresponding side lengths, we're given the areas of each of these similar figures. So instead of finding the similarity ratio first, then finding the ratio of the perimeters, then finding the ratio of the areas, we need to start with the ratio of the areas because that's what they give us. So we're going from small to large, meaning we want the area of our smaller triangle in the numerator and the area of our larger triangle in the denominator. We then need to simplify this fraction. What is 36 over 64 simplified down to? That would be 9 over 16. So we have found the ratio of the areas, and we need to use that in order to now find the ratio of the perimeters. Remember, if the ratio of the perimeters was a over b, then the ratio of the areas was a squared over b squared. So if we're given the ratio of the areas, to find the ratio of the perimeters, we actually have to square root the simplified ratio of the areas. So we're going to square root the 9 and we're going to square root the 16. And when we do that, we end up getting 3 over 4. That would be the ratio of the perimeters. Meaning, if I were to find the perimeter of the small triangle and put it over the perimeter of the large triangle and simplify that down, that ratio would equal 3 over 4. Lastly, we can find our similarity ratio or scale factor because it's equal to the ratio of the perimeters, which is 3 over 4. Meaning, if I were to create a ratio with a pair of corresponding side lengths, with the side length of our smaller triangle over the side length of our larger triangle and simplify that ratio down, it would give me 3 over 4. Part B, doing the same thing, and we are again given the areas of our two similar figures. So in order to find the similarity ratio, ratio of the perimeters, and the ratio of the areas, we have to start with the ratio of the areas, because that's what we're given. So we're going to set up a ratio small to large, meaning we're going to take the area of our smaller circle and put it over the area of our larger circle, and simplify that ratio down in order to get the ratio of the areas. So how does this simplify? Well, the pi's cancel out, and 2 over 200 simplifies to 1 over 100. That is the ratio of the areas from small circle to large circle. Now we can use that in order to find the ratio of the perimeters. Remember, if the ratio of the perimeters is a over b, then the ratio of the areas is a squared over b squared. Meaning, if I'm given the ratio of the areas and I want to find the ratio of the perimeters, I just need to square root the ratio of the areas. So I'm going to square root the numerator and denominator. Square root of 1 is 1, square root of 100 is 10. So the ratio of the perimeters is 1 over 10, meaning if I were to find the perimeter, or circumference in this case, of our smaller circle, and put it over the perimeter or circumference of the larger circle, and simplify that down, it would give me 1 over 10. Lastly, we need to find the similarity ratio or scale factor, which we now know is equal to our ratio of our perimeters, which is 1 over 10. Meaning, if I had the radius or diameter of this smaller circle, and I put it in a ratio over the corresponding radius or diameter of this larger circle, and simplified that fraction down, or ratio down, it would equal 1 over 10. Time for a U-try! Okay, doing the same thing. And again, we are given the areas, so we need to start by finding the ratio of the areas. Remember, we are going from small to large, so we're going to take the area of our smaller pentagon in this case and put it over the area of our larger pentagon. We then simplify that fraction down, or ratio down, and we end up getting 25 over 81. That is the ratio of our areas. Now we can use that in order to find the ratio of our perimeters. Remember, if the ratio of our perimeters is a over b, then the ratio of our areas is a squared over b squared. So to find the ratio of our perimeters, we just square root the ratio of the areas. Meaning, we just square root the numerator and denominator here, and we get that the ratio of our perimeters would be 5 over 9. Meaning, if I were to find the perimeter of this smaller pentagon and put it in a ratio over the perimeter of our larger pentagon here, and simplify that ratio down, I would get 5 over 9. Lastly, we want to find the similarity ratio or scale factor, and that's just going to be equal to the ratio of the perimeters, 5 over 9. Meaning, if I were to create a ratio with a pair of corresponding side lengths, with the side length of our smaller pentagon over the side length of our larger pentagon, and simplify that ratio down, it would equal 5 over 9. Part B, doing the same thing. We again want to find the similarity ratio, ratio of the perimeters, and the ratio of the areas, but we're given the ratio of the areas. So we have to start by finding the ratio of the areas. So we take the area of the smaller circle and put it in a ratio over the area of the larger circle. We then simplify this down, the pi's cancel out, and 25 over 900 simplifies down to 1 over 36. That is the ratio of our areas here. Next, we want to find the ratio of the perimeters. And we remember, if the ratio of the perimeters is a over b, the ratio of the areas is a squared over b squared. So if we're given the ratio of the areas and we want to find the ratio of the perimeters, we just need to square root the ratio of the areas. So we're going to square root the numerator and denominator. Square root of 1 is 1, square root of 36 is 6, meaning the ratio of the perimeters is 1 over 6. So what that means is that if I were to find the perimeter, or circumference in this case, of our smaller circle and put it in a ratio over the perimeter, or circumference in this case, of our larger circle, and simplify that ratio down, I would get 1 over 6. Lastly, we need to find the similarity ratio or scale factor, which we know is just equal to the ratio of the perimeters, 1 over 6. Meaning, if I had the radius or diameter of this smaller circle and I put it in a ratio over the corresponding radius or diameter of this larger circle and simplified that ratio down, I would get 1 over 6. Now example 3 says, for each pair of similar figures, find the scale factor of the large to the small rectangle. Then find the area of the smaller rectangle. So the first thing we need to do is find the scale factor of the large to the small rectangle. So in order to find the scale factor or similarity ratio, what you need to do is create a ratio of the pair of corresponding side lengths here. Since we're going from large to small, we need the side length of our larger rectangle over the side length of our smaller rectangle. We then simplify that ratio down, and we end up getting that our similarity ratio or scale factor is equal to 6 over 1. Next, this wants us to find the area of the smaller rectangle. So here's how this works. The first thing we're going to have to do is find the ratio of the areas here. Now remember, the ratio of the areas is equal to the square of the similarity ratio or scale factor. So if I take this similarity ratio or scale factor, 6 over 1, and I square it, I end up getting 36 over 1. Meaning the ratio of our areas is 36 over 1. Meaning if I were to create a ratio and put the area of the larger rectangle in our numerator and the area of our smaller rectangle in the denominator and simplify that down, it would equal equal 36 over 1. Now the question is, how does that help us? Well, what I can do now is I can actually set up a proportion in order to solve for this missing area. So I'm going to give this missing area a variable. I'm going to call it x. So in order to solve for x, the area of our small rectangle, we're going to set up a proportion. So it's going to have two fractions with an equal sign in the middle. On one side of the equal sign, our ratio or our fraction is going to be the ratio of the areas, 36 over 1. On the other side, then we're going to have a ratio or fraction with the corresponding actual areas here. So if we're going 36 over 1, meaning large to small, on the other side of the equal sign, we should have the actual area ratio, which would be large to small. So 324 inches squared over x, because we're trying to find the area of this smaller rectangle. Now all we have to do is just solve this proportion in order to solve for the area of our smaller rectangle. So how do we solve a proportion? Well, we cross multiply. When I cross multiply, I end up getting 36x is equal to 324. I then divide both sides by 36 to solve for x, and I get x is equal to 9 inches squared, or 9 square inches, meaning that the area of the smaller rectangle is 9 inches squared, or 9 square inches. You try. Okay, doing the same thing. First, we want to find the scale factor of the large triangle to the small triangle. So, in order to find the scale factor or similarity ratio, what you have to do is set up a ratio between the corresponding side lengths of these two similar triangles. And since we're going from large to small, we want the side length of our larger triangle over the side length of our smaller triangle. We then simplify that ratio down, and we end up getting the similarity ratio or scale factor between these two similar triangles is 3 to 2. Next, we want to find the area of the larger triangle. So, in order to find the area of the larger triangle, we need to first determine what the ratio of the areas between these two triangles is. So in order to determine the ratio of the areas, all we have to do is just square our similarity ratio. So we square the numerator and denominator over here. We get that the ratio of the areas between these two similar triangles is 9 over 4. Meaning, if I were to find the area of our larger triangle and put it over the area of our smaller triangle and simplify that ratio down, it will be 9 over 4. Now, how does this help us? Well, what we're going to do is we're going to set up a proportion in order to solve for this missing area. So the missing area here is the area of our larger triangle. We'll give it a variable. We'll call it x. So in order to solve for x, we're going to set up a proportion, which is two ratios with an equal sign in the middle. On one side of our proportion, one of our ratios is going to be the ratio of our areas, 9 over 4. On the other side of the equal sign, we're going to have the ratio of the actual areas, and it needs to be large over small because that's what the ratio of our areas is. So our proportion is going to be 9 over 4 is equal to x over 54 meters squared, or square meters. Now all I have to do is solve this proportion in order to find the area of our larger triangle. So we cross multiply, and when we cross multiply, we end up getting 4x is equal to 486 meters squared. We then divide both sides by 4. We get x is equal to 121.5 meters squared, or square meters, meaning that the area of our larger triangle is 121.5 meters squared, or square meters. Now example 4 says for each pair of similar figures, use the given areas to find the scale factor from the small to the large figure, then find x. So this time we are given the areas of these similar figures and we're trying to find one of the corresponding side lengths. So how do we do this? Well, since we're given the areas of each of these figures, we're going to start by creating the ratio of the areas. And remember the ratio of the areas, since we're going from small to large, we're going to put the area of our smaller quadrilateral over the area of our larger quadrilateral. We then simplify that down, we end up getting the ratio of the areas is 9 over 25. Now, how does that help us? Well, we can actually use the ratio of the areas in order to find the scale factor or similarity ratio from the small to the large figure. So if the similarity ratio is a over b, then the ratio of the areas is a squared over b squared. So if I'm given the ratio of the areas and I want to find the similarity ratio, I just square root the ratio of the areas, and I end up getting the square root of 9 over the square root of 25, which is 3 over 5. This is our similarity ratio or scale factor. Now what we can do is use this similarity ratio or scale factor in order to set up a proportion to solve for x. Remember, in a proportion, we have two ratios that are equal to each other. In one side of our proportion, we're going to have the similarity ratio or scale factor, 3 over 5. And that's going to be equal to the ratio of the corresponding side lengths, small over large. So it's going to be x over 32.9 feet. Now all we have to do is cross multiply, solve this proportion, and we'll find x. So when we cross multiply, we get 98.7 feet is equal to 5x. Divide both sides by 5, we get x is equal to 19.74 feet. You try. Okay, doing the same thing. Again, we're given the areas of these two similar figures, and we're trying to find one of the missing side lengths. So the first thing we need to do is create the ratio of the areas. And since we're going from small to large, the ratio of the areas here would be 27 centimeters squared over 147 centimeters squared. We then simplify that ratio down, and we end up getting the ratio of the areas is 9 over 49. Next, we can use that ratio of the areas in order to find the scale factor or similarity ratio. To do that, remember, the similarity ratio or scale factor, if that's a over over b, the ratio of the areas is a squared over b squared. So to go from the ratio of the areas to the similarity ratio, we have to square root the numerator and denominator here, and we end up getting the similarity ratio or scale factor is 3 over 7. Now we can use that similarity ratio or scale factor in order to solve for our missing side length. What we're going to do is we're going to set up a proportion. Remember, a proportion is just two ratios equal to one another. On one side of the proportion, one of the ratios is going to be our similarity ratio, our scale factor. On the other side, we're going to have the ratio of these corresponding side lengths. And since we're going from small to large, we need to have the small side length over the large side length. We then cross multiply, solve for x. So here, 3 times x is going to give you 3x, 7 times 5 is going to give you 35. Divide both sides by 3, you get x is equal to 35 over 3, or 11 2/3 centimeters. Now, word problem says you are building a scale model of the new park in Huntington Beach. The park is in the shape of an isosceles trapezoid with a perimeter of 9 miles. If your model has a perimeter of 12 inches, what is the ratio of the areas of the model to the actual park? If the model has an area of 120 square inches, what is the area of the actual park? So step 1 in a word problem, we're not scared, we can do this. Step 2, what is the question asking us to find? It's asking us what is the area of the actual park. So that's going to be what we're trying to find. So we'll call the area of the actual park x. That's what we're solving for. Next, let's go through the question and look at what we're given. We're given that the perimeter of the actual park is 9 miles. We're given that the perimeter of the scale model is 12 inches. We're also given that the model has an area of 120 square inches. So we should be able to use this given information in order to solve for our missing area. All we have to do is set up a ratio of the perimeters, use that to find the ratio of the areas, and then set up a proportion with the ratio of the areas to solve for our missing area. So that's what we're going to do. First, we want to find the ratio of the perimeters. Now, to find the ratio of the perimeters, what we're going to do is take the perimeter of our scale model, 12 inches, and put that over the perimeter of our actual park, 9 miles. We then simplify that down. We get the ratio of the perimeters is 4 inches to 3 miles. We can then use the ratio of the perimeters in order to find the ratio of the areas. Remember, to find the ratio of the areas from the ratio of the perimeters, you just square the ratio of the perimeters. So 4 squared over 3 squared is going to give you 16 over 9. That would be the ratio of our areas. Now what we can do is use that ratio in order to set up a proportion and solve for our missing area. So in a proportion, we have two ratios equal to each other. On one side of our equal sign, we're going to have the ratio of our areas, 16 square inches over 9 square miles. That's going to be equal to the ratio of the area of the scale model to the area of the actual park. So 120 square inches over x, because that's what we're solving for. We then solve this proportion by cross multiplying, and we get 16x is equal to 1080. Divide both sides by 16, you get x is equal to 67.5. But we were asked a word problem. Don't just leave your answer as 67.5. You need to answer in a sentence. What did we just find? We found that the area of the actual park is 67.5 square miles.